So linear search has linear performance. And the reason for that is if we do not have the element in the list, it takes us n number of comparisons. So if I have 100 elements in my list, if the thing I'm searching for is not in the list, I cannot determine that until I have examined all 100 values in the list. Because the list is unsorted, I can't make any assumptions. Now if the list is sorted, this presents a unique opportunity. So much like a phone book or a dictionary that's sorted, we can utilize that to our advantage. So for example, if you're searching for a particular name in a phone book, or if you're searching for a particular word in a dictionary, the way that we can quickly find that word is just, in our minds, we know that this is sorted, so we can just open up any page, and then we can adjust our search because we know where the word will appear based upon where we're at. It'll either be in the other half of the book or the other parts. There's two parts that our word could be in based upon where we start, and because they're sorted, we can move into and isolate and remove much of the other search space. So the idea with binary search is, assuming they're sorted, the best technique is to always pick the middle. And then, for example, if I'm trying to find either the largest or smallest value, I can then isolate and remove half of the items in my search. So in a linear search, I would have to go through all of those. But in a binary search, just the very first comparison, I can eliminate half the values in my space. So if I have a list of 1 million elements and I pick the middle, I know that I can immediately eliminate 500,000 elements that I don't have to search anymore. Because it's sorted, I know that the value I'm looking for is either on the left half or the right half. So this is a great unplugged activity that we show to our students. We do the phone book example where we tear up a phone book. And we also do an example where students can earn money. We put cups down on the floor, and inside of that we hide numbers, and we ask students to take guesses. And every time they take a guess, they need to pay me back a quarter. So I give them $2 in quarters, and every time they make a guess, they owe me a quarter back. So if they're really smart about it, they can actually win enough money to maybe go to the vending machine at the next break and in my summer camp and grab a drink. Let's now consider a concrete example of the binary search. On this slide, you can see there's a table where at the very top we have index values from 1 to 9, and we have the values that are in those particular slots. So you can think of the index as just the location of something like a mailbox number, and the value is what's actually inside of the mailbox. And in this particular case, this table is sorted from largest to smallest. So we'll use that to our advantage. So in a binary search, we want to be able to cut in half each search space each time we go through as a pass. And there's two examples here. So assume we're searching for the value 37. And in this case, the minimum index is 1, and the first pass, the maximum index is 9, because we're searching initially through the whole list. So in this case, the middle of the list would be index location 5. So I look at the value inside of 5, and I notice that it's 50. And I know that I'm looking for 37, and I also know that this list is sorted. So there's no logical way that the number 37 could appear on the left-hand side of the list from 1 to 5, because 37 is less than that, and I know it's sorted from highest to lowest. So this knowledge allows me to immediately cut my search space in half, so that on the next pass, I'm searching with the minimum value of 6 through 9. So just the right side of this particular list. And the middle, in this case, rounding up, would be 8. So I, again, look at the value inside of index location 8, which is 20, and I compare 20 to 37. In this case, I know that 37 is greater than 20. So if this number exists at all in the list, it must be to the left of 8, index location 8, and it must be to the right of index location 6. So what I do is I then reset. The minimum would be 6, the maximum would be 7, and in this case the middle of that rounding up would be 7. I look at location index 7 and I find the value of 37, which I can now declare victory because that's the actual value I'm searching for. So I could return even the index 7 as a result, or I can declare this value, I could pass back true to indicate that the number is in there. So I only needed 3 comparisons to do that. If I did a linear search, that would take 7 comparisons. So I hope you can see that the performance of the binary search is much better than that of the linear. Let's look now at a case where 82 is the desired thing we're looking for in the list. So in a linear search, this would take at least 9 comparisons. because I'd have to search through every element of the list to determine that it's not in there. Okay, linear search, again, can work with things that are not sorted. But in a binary search, I can use this, again, to advantage the fact that this is sorted. And I begin in my pass 1 again with minimum index 1, maximum index 9, and the middle was 5. I look at the value of 5, again 50, and the value I'm looking for, 82, is greater than 50. So now I know in this example I can totally remove the right side of the list. So I'm looking now from location 1 through 4 and trying to find the value of 82. Now, of course, you and I can look at this table and determine 82 is not in there. But how do we program or algorithmically express that? It's one thing for us to use our vision to do that. It's another thing to describe that computationally. So in the second pass now, min is 1, max is 4, and rounding up the index in the middle would be 3. So looking at the value at index location 3 being 83, and I'm looking for 82, I know that it must be the case that 82 is to the right of index location 3. And so I update min to be 4, max is 4, and therefore the middle is 4. Now when I go in my algorithm, if I look at 4, I determine 77 is the value, and that's not 82. And eventually what happens, my min and max become equal when I don't find the value, and I can declare not found. So this took 3 comparisons, where a linear search would have taken 9 comparisons. So hope you can see the performance there that can be gained if the list is sorted. But of course it costs performance time computationally to sort the list as well, as we studied in the previous lesson. So here is the binary search algorithm in a sort of pseudocode, where in this case we're assuming the list is in descending order from high to low, just like we saw on the last slide. And the condition that we use to continue searching is whether we found the item we're looking for, or the case when the minimum index becomes greater than the max. And so in this case, I always start in the middle. So the middle is equal to the max plus the min divided by 2. I then do a search. If the value I'm looking for is equal to the middle that I just picked, then found is true, and I can declare victory and know that the element is in that list. Otherwise, I need to adjust the min and max index values as I did on the previous slide. And this continues to repeat until that condition is met of being found as true, or min becomes greater than max. And this is a much more improved search algorithm than linear search. In this slide, we look at the binary search as implemented in Snap. So again, I will leave you with the exercise of tracing through this on your own and trying to understand this. It's very similar to the pseudocode on the previous slide, but I'd like you to look at this code and try to understand how the binary search is working. Again, we have local variables being used rather than global variables, but you should see a one-to-one correspondence almost in many cases back to the pseudocode. So again, this is why it's helpful to have our students write down their algorithms, their programs initially in pseudocode or flowcharts, and then they can see the correspondence as it translates over into Snap. So this concludes the discussion of algorithms, a very important topic that helps to understand the complexity of the computations that we're performing, and something that you'd like to probably go more deeply into in your course. So we'll provide some links to that in the actual lesson. But we wanted to use these 2 ideas of searching and sorting to help you understand the notion of performance in terms of space and time complexity.